Hi guys, we're doing section 5.3 today, the properties of logarithms. These are the properties of logs that we're going to be using. B is positive, the base is always positive. We've already talked about that, but it can't equal 0. And U and V are going to represent positive numbers. Remember, we can only take the log of a number that's greater than 0. And then R is any real number. Product rule for logarithms. Notice we start with one log, with product means multiplication. And we can break this into two separate logarithms. We break it into the log of U plus the log of V. Multiplication becomes addition. One log becomes two logs. Quotient rule. Division. This is what we're dividing. It's the log of U minus the log of V. And the power rule, all you do is you take this exponent and you bring it right around the front. Now, sometimes people make certain mistakes. Let me point them out real quick. Let's say we have log base B of U plus log base B of V. This is not equal to the log base B of U times the log base B of V. More often, I see division. If I have a subtraction, I see people put them together as log base B of U divided by log base B of V. That again is not true. Notice we're going from two logs on this side to one log, not to two logs. So this is really important to remember, that we're not multiplying logs or dividing logs, just the values that are inside the log. Another mistake is that the log base B of U plus V is not equal to the log base B of U plus the log base B of V. The log does not distribute. It's a function. Functions don't distribute. We have the product rule, the quotient rule, and the power rule. We do not have a rule for sums. Here with the natural log, I have the natural log of 5 plus the natural log of x. Because it's multiplication, 5x means 5 times x. All I have to do is separate it into two separate pieces. Now, B is similar but a little different, and I'll show you why. Log base 2 of 8 plus the log base 2 of x. Remember that if we can simplify, we want to simplify. This is the same as log base 2 of 2 to the third power plus the log base 2 of x. Log base 2 of 2 cancel, and that's equal to just that exponent, or x. My final answer here would be 3 plus log base 2 of x. It is really important to be able to see when you can simplify. Now we have a new rule, which is the power rule. So if we have the log base B of U to the R, then that's equal to R times the log base B of U. Here, another way to do this would be if we start here with the log base 2 of 2 to the third plus log base 2 of x, we can take this exponent and bring it around to the front using the power rule. And then I would get 3 log base 2 of 2 plus log base 2 of x. When the base and the argument match, this equals 1. 1 times 3 is 3. Our final answer would be 3 plus log base 2 of x. Either way, we get the same answer, but there are two different ways now because we have another rule that we haven't had before. Let's use our quotient rule. Our quotient rule says if we have the log base b of u divided by v, that's equal to the log base b of u minus the log base b of v. Here, this becomes the log base 5 of 12 minus the log base 5 of x, okay? And again, I looked at my 12, and 12 is really the same as 3 times 4. 4 is the same as 2 times 2. I don't really have this to a power. I do have 2 squared times 3. Simplify it a little bit, but it's not enough to make it worth it. But let me just show you what I could do. This is the same as the log base 5 of 3 times 4 minus log base 5 of x. This is the same as the log base 5 of 3 plus the log base 5 of 4 minus the log base 5 of x. So all I did is now I use the product rule because I have 3 times 4, which is a product. I could also say that this is equal to 2 squared. And I could then use my power rule. And what the power rule does is it takes the exponent and brings it over to the front. I would get 2 log base 5 of 2 minus log base 5 of x. Would I do this? Probably not, because it's not all that helpful. I didn't get rid of any logs like I did in the previous example. In the previous example, I completely got rid of one of the logs and made it a 3. Here, I'm really not getting rid of any logs. Now, if that was a base 2, it would be very helpful. This becomes, now there's no base. What is the base? Hopefully you said 10. This is the common log. When there's no base, we assume it's 10. This is the log of x minus the log of e to the 5th power. Well, I definitely want to fix that because we don't leave exponents when we simplify. We're going to take this 5, which is my exponent, and I'm going to bring it around to the front, and I get 5 log e. If I had the problem as ln of x over e to the 5th, then this is ln of x minus ln of e to the 5th, which is equal to ln of x minus, again, I'm using my power rule, 5 ln of e, but ln is base e. ln of e is 1, which gives me ln of x minus 5. So the power rule again just says that if I have the log of u to the r power, that equals r log u. All I'm doing is taking this exponent, bringing it around to the front. That's why I get 3 log 6. And for b, well, let's rewrite this as the log base 1/2. And remember that x is the same as x to the 1/4 power. And if I have n m, which is the same as nx to the m, both of those are the same as m over n. Since the exponent on x is 1, I get 1/4. Now, I use my power rule, and I get 1/4 times the log base 1/2 of x. Let's use properties of logarithms to expand each logarithm expression as much as possible. Number one, product rule, the log, and I'm not going to put the base, but it doesn't matter what the base is. It's u plus log of v. The quotient rule is if I have the log of u over v, that equals the log of u minus the log of v. And the power rule is the log of u to the r equals r log. We're not going to use the quotient rule, but we're definitely using the product and the power rule. I would recommend we just start separating all the products. What's inside here is really 49 times x to the third times the fifth root of y squared. So I'm going to make 3 different plus signs for each one of those variables and the constant. I'll keep the constant separate as well. I do know something about 49, don't I? 49 is the same as 7 times 7. So whenever you look at a number, you always want to see, is there some exponent that makes that work? And we found one. And then this, for the second one, I'm going to use the power rule because I have that exponent. So I'm going to bring that around to the front. And then I just have log base 7 of x. Plus, again, log base 7. And I'm going to use my rule for radicals. This is the same as y to the 2/5. And if you don't know how I got that, go back to the previous slide and look at the rule for radicals. Here, there's 2 ways to do this. I could either bring this around using the power rule, or I can use the property of logs where these cancel. Either way, it's going to be 2. I think I'll use the property of logs. I'll just make this 2 plus 3 log base 7 of x plus, I still have an exponent in the last term. So I'm going to bring that around to the front by using my power rule. That's about as simple as it gets. I don't have any multiplication. I don't have any exponents. I don't have any division. That's it. I'm complete. Here we have a division. And whenever I have division, that's the first thing I really want to do. This is equal to ln of x squared minus 4 minus ln of 9ex cubed. Using my quotient rule, which is subtraction, I just separated the numerator and the denominator from each other. Then the next thing I do, I have the natural log of x squared minus 4, but I can actually factor x squared minus 4. That's equal to x plus 2 times x minus 2 minus ln of, I'm going to separate this 9 times e to the x cubed from each other using the product rule. Ln of 9 plus ln of e x cubed. Now I have a product again. I have ln of x plus 2 plus ln of x minus 2 minus parentheses ln of 9 plus, well, I have ln of e to the x cubed. Even though this is x cubed, it's still my exponent on e, so I can bring it to the front and I can make this x cubed ln of e. That equals ln of x plus 2 plus ln of x minus 2. I'm going to distribute here. I get minus ln of 9. And since the base of ln is e, it's not going to help me with ln of 9. It's not going to help me reduce it at all. I can make it 3 squared, but I still don't know the answer without a calculator. So if I'm going to use a calculator, I might as well just put in 9 minus x cubed, but ln of e is equal to 1. If the base and the argument are the same, it's always 1. Log base e of e is 1, which means ln of e is 1. There's really nothing more to do. Remember, I don't have a sum rule, so I can't change the x plus 2 and x minus 2. This is equal to minus ln of 3 squared minus x cubed, which gives me x plus 2 plus ln of x minus 2 minus 2 ln of 3 minus x cubed. This definitely is the final step. Now we're going to go the opposite direction. You don't have to rewrite it unless you want to. If I see the log of 2 values with the same base added together, I can turn that into 1 log of u times v because I have the product rule. I can do the same thing with the quotient rule. If I have minus there, remember I'm turning into 1 log. It just is u divided by v. And the power rule, I would have r log of u. I take the number in front and I make it an exponent. That would equal log of u to the r. Step 1 is going to be power rule. I'm always going to use the power rule first because I can't do anything as long as I have those constants in front of the logs. To use the power rule, this is equal to the log of x minus 1 to the 1/2 power minus the log of z cubed plus the log of 5. So that's my first step. What I'm going to do for my second step is I'm going to take all positive to the beginning. I'm going to rewrite this as the log of x minus 1 to the 1/2 plus the log of 5 minus the log of z to the 3rd power. Because now I know these two are multiplied together. This becomes the log of 5 times x minus 1 to the 1/2 minus the log of z cubed. And now I'm going to do my division. This is equal to the log of 5 times x minus 1 to the 1/2 power divided by z cubed. Or you can turn this into 5 times the square root of x minus 1 over z to the 3rd power. Because that 1/2 really is the same as saying the square root. And now we've got everything into 1 log. The first thing I'm going to do is I'm going to distribute this. Is 2/3. There's absolutely more than one way to do all these problems. The next thing I'm going to do is I'm going to bring my positives to the front. I have 1/3 log base 3 of x plus log base 3 of 10 minus 2/3 log base 3 of y. I can't have coefficients to use my rules, so I have to use my power rule. This is equal to the log base 3 of x to the 1/3 power plus the log base 3 of 10 minus the log base 3 of y to the 2/3 power. Now, this is my numerator. and this is my denominator. This becomes the log base 3 of x to the 1/3 times 10 minus log base 3 of y to the 2/3. This becomes the log base 3 of 10x to the 1/3 divided by y to the 2/3. Or this is equal to the log base 3 of 10 times the cube root of x over y squared. Remember, what you want to do is read how they want to input. If it says use radicals, use radicals. If it says use fractional exponents, use fractional exponents. If it doesn't say, then it doesn't matter. It'll accept both. Remember, we had that equality property for exponents where we said if b to the x equals b to the y, then x equals y. Well, we have one like that for logs. So let's solve these. Well, I have the same log base 7 on both sides, and they're equal, which means that x minus 1 has to equal 12. I add 1 to both sides, and I get x equals 13. We don't have the log equals the log, do we? We have to use our power rule to say that the natural log of x squared equals the natural log of 16. Now our logs are the same. X squared equals 16. I take the square root of both sides. X equals plus or minus 4. So that means x equals positive 4 or x equals negative 4. Now it's really important, this is really important. Before I give my answer, I always plug it back in. Oh, let's do 4, natural log of 4. Okay, that's no problem, I can do that. Can I take the natural log of a negative value for x? No, this is not a solution. Even though it's one possibility, it still is not a solution. Remember, the domain of the log function is x has got to be greater than 0. Before I started rearranging things, it was in its most simple form. If I plug in negative 4 to this x value, I'll be trying to take the natural log of a negative number, which does not exist. And the only solution here is x equals 4. Have a good rest of your day. Thank you.